new on Curiosity Stream.
I'm James Burke. I'm going to take you on a journey through time.
James Burke's visionary series returns, reimagined for our time.
Now, this is all uncharted territory.
The Washington Post hails Burke as one of the most intriguing minds in the Western world. The New York Times raves he careens from one great moment in history to another.
Where do we want to go from here?
Experience all new connections.
So what's the next connection?
With monthly, annual, and bundled plans, find the one that works for you at curiositystream.com.
Hello, Saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
This is SpaceTime, Series 23, Episode 124, full broadcast on the 20th of November 2020. Coming up on SpaceTime, a new look at the early life of Jupiter and Saturn, why the Earth's moon is rusting, and studying climate change and weather from space. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study claims to have narrowed down the likely original orbits of the gas giants Jupiter and Saturn. The findings by Matt Clement from the Carnegie Institute refine science's understanding of the forces which have determined our solar system's current architecture. The research also supports the idea of a third ice giant orbiting along with Uranus and Neptune, but which was eventually ejected from the solar system early in its history. Clement's findings suggest that this ejection ensured that only small rocky planets like the Earth formed inwards of Jupiter. The Sun was formed in the centre of a spinning protoplanetary disk, with some of the material in that disk coalescing to form planets. Clement says the orbits of the early formed planets were thought to initially be closely packed and circular. But gravitational interactions between the larger objects perturbed the arrangement and caused the infant giant planets to rapidly reshuffle, eventually creating the configuration we see today. Clement says the arrangement of the planets in our solar system is highly unusual, and so he used models to reverse engineer what he saw in order to replicate the formation process. He describes it as being a bit like trying to figure out what happened in a car crash after the fact. How fast were the cars going? In which directions, and so on. Clement and colleagues conducted some 6,000 simulations of our solar system's evolution, eventually discovering an unexpected detail about Jupiter and Saturn's original relationship. Jupiter in its infancy was thought to orbit the Sun 3 times for every 2 orbits that Saturn completed. But the authors found that this 3-2 resonance couldn't satisfactorily explain the configuration of the giant planets as they're seen today. The authors' models showed that a ratio of 2 Jupiter orbits to 1 Saturnian orbit more consistently produced the results that look like our familiar planetary architecture. Clement says this indicates that while our solar system is a bit of an oddball, it wasn't always the case. He says establishing the effectiveness of this model will help in research looking at the formation of the terrestrial planets, including the Earth, and perhaps even provide clues about what to look for in exoplanetary systems, which could potentially harbour life. The model also showed that the positions of Uranus and Neptune were shaped by an ice giant planet that was kicked out of the solar system in its infancy, and by the mass of the Kuiper Belt, the icy region on the solar system's edges composed of dwarf planets and planetoids, of which Pluto is one of the largest members. For years, there's been growing evidence that planetary systems, including our own solar system, aren't stable, but rather are subjected to a process of planetary migration during their birth in early history. The thing is, there are a lot of planets out there containing materials which aren't likely to condense out of the protoplanetary nebula at their current orbital distances from the host stars. Observations of exoplanetary systems have found evidence of numerous giant Jupiter-sized planets circling so close to their host stars it takes just a few days or even a few hours to complete each orbit, environments which are far too hot for planetary formation. These so-called hot Jupiters must have formed further out and then over time migrated inwards to their present locations. And astronomers have seen evidence of similar planetary migration in the Sun's solar system as well. The Nice model and variations of it, such as the Grand Turk hypothesis, have been developed to explain specific features such as the composition of bodies in the main asteroid belt between Mars and Jupiter and features in the more distant Kuiper belt and Oort cloud. It also explains an event known as the Late Heavy Bombardment, which occurred some 3.9 billion years ago. The apparent swapped orbital positions of the planets Uranus and Neptune, and Jupiter's family of Trojan asteroids. The Grand Turk hypothesis suggests that Jupiter underwent a two-phase migration after its formation 4.6 billion years ago, near what's known as the snow line, about 3.5 astronomical units out from the Sun. An astronomical unit is the average distance between the Earth and the Sun, roughly 150 million kilometres, or 8.3 light minutes. The snow line is a region out from the Sun beyond which water usually only forms as ice. After clearing a gap in the protoplanetary gas disk, Jupiter began migrating inwards to about 1.5 astronomical units, before reversing course and migrating outwards again. If uninterrupted, this inwards migration would have left Jupiter in a close-in orbit around the Sun, like recently discovered hot Jupiters in other planetary systems. Saturn also migrated towards the Sun, but being smaller, it migrated faster, converging on Jupiter and being captured in a 2-3 resonance with Jupiter during its migration. A gap in the gas disk then formed around Jupiter and Saturn, altering the balance of forces on these two planets, which then began migrating together. Saturn partially cleared its part of the gap, reducing the torque exerted on Jupiter by the outer gas disk as Jupiter reached between 1.5 and 2 astronomical units out from the early Sun. This caused the net torque on the planets to become positive, and they began migrating outwards. The outwards migration continued because interactions between the planets allowed gas to stream through the gap, exchanging angular momentum with the planets during its passage, in the process adding to the positive balance of torques and moving mass from the outer disk to the inner disk, allowing the planets to migrate outwards relative to the disk. The transfer of gas to the inner disk also slowed the reduction of the inner disk's mass relative to the outer disk as it accreted onto the Sun. And this is important because it allowed enough material to remain to form the inner terrestrial planets Mercury, Venus, Earth and Mars. The outward migration of Jupiter and Saturn continued until they reached a zero torque configuration within a flared or dissipated gas disk at or near Jupiter's current orbit, some 5.2 astronomical units out from the Sun. Jupiter's grand tack resolves the Mars problem by limiting the amount of material available to form Mars. You see, some simulations of the formation of the terrestrial planets had ended with Mars being similar in mass to the Earth, instead of its actual mass, which is just a third that of the Earth. Jupiter's inward migration alters this distribution of materials, driving planetesimals inwards to form a narrow dense band with a mix of materials inside one astronomical unit, leaving the Mars region largely empty. Planetary embryos quickly formed in the narrow band, creating the two larger terrestrial worlds, Venus and Earth, over a period of just 60 to 130 million years. And the remaining scattered material left outside this band eventually formed the two lower mass terrestrial worlds, Mars and Mercury. The model also demonstrates how Jupiter and Saturn drive most asteroids from their initial orbits during their migrations, leaving behind an excited remnant derived from both inside and outside of Jupiter's original location. Before Jupiter's migrations, the surrounding regions contained asteroids which varied in composition with their distance from the Sun. Rocky asteroids dominated the inner region, while more primitive and icy asteroids dominated the outer region beyond the snow line. But as Jupiter and Saturn migrated inwards, about 15% of the inner asteroids are scattered outwards into orbits beyond Saturn. But after reversing course, Jupiter and Saturn first encountered these objects, scattering about 0.5% of the original population back inwards and onto stable orbits. The encounters with Jupiter and Saturn leave many of these captured asteroids with large eccentricities and inclinations. Some of the icy asteroids are also left in orbits crossing the regions where the terrestrial planets would later form, allowing water to be delivered to the accreting planets through asteroid impacts. The absence of any close-orbiting super-Earths in our solar system may also be the result of Jupiter's inward migration, which captured planetesimals, causing catastrophic collisional cascades, with the resulting debris spiralling inwards towards the Sun and taking any forming super-Earths with them. The 4 existing terrestrial planets would then have formed out of the remaining orbital debris left behind as Jupiter and Saturn migrated back out. This is SpaceTime. Still to come. Scientists think they may have solved one of the moon's little mysteries, how an airless, bone-dry world can rust. And studying climate and weather from space. All that and more coming up on SpaceTime.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
Okay, let's take a break from our show for a word from our sponsor, ExpressVPN, rated number 1 by TechRadar. You may be wondering why you need a virtual private network. Well, it's in the name. It's all about privacy. Do you really want big brother tech companies, hackers, governments, and who knows who else snooping in on your online activities? Now, you might not have anything to hide, but it's still really creepy, and it could be dangerous for you and those you care about. Also, how often do you run across a website and you want to get information from it, but you find out that they're geo-blocked? It's all very frustrating, and it's becoming an increasing problem. And that's where ExpressVPN can help you. ExpressVPN's a simple and efficient way to protect your online privacy. It's internet without borders from the world's leading VPN provider. So, protect your online privacy today. And find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more. And of course, you'll find the link details in the show notes and on our website. That's tryexpressvpn.com/space. And now, it's back to our show.
You're listening to SpaceTime with Stuart Gary.
Scientists think they may have solved one of the moon's little mysteries, how an airless, bone-dry world can rust. The question first arose after astronomers studying the chemical composition of the moon detected the presence of hematite, a form of iron oxide or rust that normally forms on iron in the presence of oxygen and water. Mars has long been known for its rust. That's why it's the red planet. Iron on its surface, combined with water and oxygen in its ancient past, reacted to form the vast slabs of hematite which cover much of the Martian landscape. But the discovery of rust on the lunar surface came as a complete surprise to scientists. The hematite was detected by NASA's Moon Mineralogy Mapper or M3 instrument aboard the Indian Space Research Organization's Chandrayaan-1 orbiter, which discovered water ice on the moon and mapped out a variety of lunar minerals while surveying its surface in 2008. Liquid water interacts with rock to produce a variety of minerals, and M3 detected spectra suggesting the poles had a very different composition compared to other parts of the moon. The study's lead author, Shui Li from the University of Hawaii, says he was intrigued by the findings and honed in on these polar spectra. While the moon's surface is littered with iron-rich rocks, Li says he was still surprised to find such a close match with the spectral signature of hematite. The problem is the moon's not supposed to have oxygen or liquid water. So, how can it be rusting? The mystery begins with the solar wind, the constant stream of charged particles flowing out from the sun, which bathes the solar system, including the Earth and Moon, with hydrogen. And the thing is, hydrogen makes it harder for hematite to form, because it adds electrons to materials it interacts with. And the thing is, for iron to form rust and to form hematite requires an oxidizer which removes electrons. And while the Earth has a magnetic field shielding it from this hydrogen, the Moon does not. So, Lee turned to JPL scientist Abigail Freeman and Vivian Sun to help him work out what's going on. The hypothesis eventually developed by the trio and reported in the journal Science Advances suggests that while the moon lacks an atmosphere, it does have an exosphere, an extremely thin layer of gases near the surface which include trace amounts of oxygen. That oxygen comes from the Earth by way of the planet's magnetotail, a comet-like tail of the Earth's magnetic field stretching out from the night side of the Earth, guided by charged particles in the solar wind. Earlier studies had already discovered that oxygen from Earth's upper atmosphere can hitch a ride on this trailing magnetotail, travelling the 385,000 kilometres to the Moon. And this all fits in with the M3 data, which found far more hematite on the Moon's Earth-facing or near side compared to its far side. And the combination of these two factors would open occasional windows during the lunar cycle when rust can form. As for the water needed to complete the process, well, it's not coming from the cold sinks or the shadowed craters known to contain water ice, but instead from water molecules found on the lunar surface. Lee proposes that fast-moving dust particles that regularly pelt the Moon could release these surface-borne water molecules, mixing them with iron in the lunar soil. And heat from these impacts could increase the oxidation rate. The dust particles themselves may also be carrying water molecules, implanting them into the surface so that they mix with iron. So, during just the right moments, namely when the Moon's shielded from the solar wind and the oxygen is present, a rust-inducing chemical reaction could occur. Still, much more data is needed in order to determine exactly how the water is interacting with the rock. And that data could also help explain another mystery: why smaller quantities of hematite are also forming on the far side of the Moon, where Earth's oxygen shouldn't be able to reach it. The model could also help explain hematite found on other airless bodies such as asteroids. Little bits of water and the impact of dust particles could be allowing iron on these bodies to rust as well. To find out more, Andrew Dunkley speaking with astronomer Professor Fred Watson.
What's happening to the Moon? Why is it rusting?
Well, the Moon's going rusty. It's not all of the Moon, it's certain parts of the Moon. But what's happened is there has been a reanalysis of data from the Chandrayaan Moon mineralogy mapper, which flew. Chandrayaan was several years ago. It's an Indian Space Research Organization spacecraft orbiting the Moon, discovered water ice on the Moon, and it essentially mapped out the minerals. It had this mineralogy mapper on board. And so there has been basically a reanalysis of some of the data that have come back from that. And what has emerged from that is signs of hematite, which is an oxide of iron, which is effectively rust. But hematite is present on the Moon, probably in small quantities, but it was detected by the mineralogy mapper instrument. And it's a puzzle to understand how it gets there, because for hematite to form, you need oxygen. And the Moon is not well placed for oxygen. It's got this hydrogen there, which is released by the water ice that's on the Moon, but not oxygen. And so the puzzle has been to try and understand why that hematite is there. The research that's been done actually suggests that the oxygen comes from the Earth, basically is transported along the Earth's magnetic field. So you've got to get this picture in your mind of what that magnetic field looks like. We're used to bar magnets having a magnetic field, and probably imagine the field lines being those kind of circular things. I'm waving my hands around here, Andrew. Not even you can see me, so let alone our listeners.
I could hear it, though.
Oh, you could hear it.
I could hear it.
Oh, that figures. Anyway, you know what a magnetic field looks like, but the Earth's magnetic field is highly distorted, and so the magnetic field sort of trails behind it. And the analogy that's usually used is it's just like a windsock. You know how a windsock points away from the direction that the wind's coming from. Likewise, the solar wind, the Earth's magnetic field trails behind it. And of course, the Moon passes through that every month, basically. It passes through that windsock as it goes around the Earth. And that is the suggestion as to how the oxygen has got there, which has reacted with the iron to form this hematite. Really quite an extraordinary story, and it might sound a little bit speculative, and maybe it is, but it is a model that works. The calculations that have been done on the possibility of this happening all come out positively. So it's big news. We can go iron mining on the moon. Maybe not, because there's no...
Oh, wonderful. You see, people probably, and I'd be guilty of this, think that once you get to the limit of the atmosphere, that's where the oxygen stops. And as you do increase your altitude, the oxygen levels decrease significantly, and that's why they have to have oxygen supplies for those high altitude aircraft and some of the daredevils who go up there to just jump off a platform for the fun of it. But it seems that there is some form of oxygen going well beyond that. That's right. That seems to be the indication.
Extraordinary, yeah.
That's Dr. Fred Watson, an astronomer with the Department of Science, speaking with Andrew Dunkley on Space Nuts. And this is Space Time. I'm Stuart Gary. Still to come, studying climate and weather from space. And later in the Science Report, the 6th Australian State of the Climate Report warns of more droughts and heatwaves for Australia due to the growing effects of climate change. All that and more still to come on Space Time.
Hello, Saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
Scientists are seeing an increasing level of global warming on Earth brought about by anthropological climate change. The scientific evidence supporting the existence of climate change is now indisputable. But how can you really tell that it's not just the weather? Andrew Shepherd from the University of Leeds is a leading climate scientist working with ESA and NASA. In this report from ESA TV, Shepherd explains how scientists separate the effects of weather versus climate from the data records and the role of space in studying changes to the Earth in real time.
Hello, my name is Andy Shepherd. I'm a climate scientist. I work at the University of Leeds in the UK, but I also work closely with the European Space Agency. So weather and climate are very different things. The easy way to think about the difference between them is just time. So weather happens to us on a day-to-day basis, and one year on today's date it might be snowing, and another year it certainly won't be. And so the things that happen on short time periods are the weather that affects us, whereas the things that happen over long time periods, longer than seasons, so maybe decades or even longer, they're climate. And it's difficult to separate these effects from climate data records, whether they're collected by a thermometer on the ground or by an aircraft in the sky or by a satellite in space, unless you have a long-term record. And that's what we aim to do, have many decades worth of measurements of whatever parameter we're measuring, so that we can separate out the effects of weather and climate. And it's important to be able to do that because weather is quite erratic, but also is a very large signal that changes quite significantly, and often the climatic changes are much smaller. So you'll be familiar with Earth's temperature change over the past centuries, really a fraction of a degree centigrade or just over that. And that's a hard signal to detect when we have 20 or 30 degrees centigrade change in temperature on the planet each year. And we need long-term records to be able to do that. That's where the cryosphere helps, because it changes quite rapidly, even if Earth's temperature changes by only a small amount. So small changes in ocean or air temperature in the polar regions will cause ice to melt. And the easy way to separate the effects of weather and climate in the polar regions are just to think really simply about snow and ice. Snow is generally what we would consider to be weather, whereas ice is the long-term storage of snow as it compacts and moves through glacier systems. And becomes part of the climate record. And if we see changes in ice on Earth today, then they tell us about changes in climate. Antarctica has told us actually a huge amount about climate change in recent decades. So what we found is that parts of the Antarctic ice sheet are flowing too quickly into the oceans. because the ocean around them is too warm, and that's causing them to be unstable. At times that causes ice shelves to collapse and break away from the continent and drift out into the Southern Ocean. And at other times it causes glaciers to speed up and to move more ice out into the oceans than can be replenished by the snow that falls inland. And that causes a difference in the amount of ice stored in the continent. And that really is simply just a difference in sea level rise, because that ice ends up in the oceans. And then anybody around the planet that has a coastline or visits a coastline or depends on a coastline for parts of their lives is affected by that. And we're instantly affected by ice losses from Antarctica, no matter where we are around the planet. So it's really important for us to, first of all, understand how the Antarctic ice sheet is changing, but more importantly, to be able to predict how the ice sheet will change in the future so that we can plan our lives around that. We've learned a huge amount about the polar regions thanks to satellites in space over the past 30 or 40 years. Some of the iconic stories that we've learned about are retreat of sea ice in the Arctic. That's been progressive during the satellite era, loss of about 10% per decade, melting of the Greenland ice sheet, and in some cases extreme melting in very hot summers, and acceleration of Antarctic glaciers. And we've learned about all of these things thanks to satellite measurements. People have visited these places, but it's actually really challenging to be able to monitor the polar regions in anything like the level of detail that's required for several really obvious reasons. First of all, it's a very inhospitable part of our planet. It's cold almost all year round. And it's dark for half of the year as well. So it's really difficult to even exist in these locations. But more importantly, they're vast. They're huge places that can't realistically be monitored on the ground, on foot certainly, from the air or from ships even, because they can't travel over sufficiently large distances to be able to monitor the signals of change, which are affecting huge parts of these areas. So we depend heavily on satellite measurements to be able to monitor in all weather conditions. Well, we've got a great deal of gratitude to the European Space Agency and other international space agencies for two things. The first one is for designing and launching missions into space. And they started that many, many decades ago. It takes typically 10 or 20 years to even get an idea for a satellite mission off the drawing board and into space. And it's thanks to people that were designing these sensors in the 1970s that we had records in the 1990s and that we can look back on them. But the space agency is doing more than just that. They're creating, and have been for some time now, fundamental climate data records of how our planet is changing from day to day, from year to year, and from decade to decade. And it's only thanks to these high quality and long-term records of climate change that we can put together the jigsaw puzzle of how our planet is changing. In the polar regions, it's become really, really essential to have these measurements and the long-term measurements. So we rely upon these measurements more than you might think to be able to predict how sea levels will change in the future and how much more our planet will warm in the future, as well as being able to monitor the changes that are happening today.
And time now to take another brief look at some of the other stories making news in science this week with the Science Report. The 6th Australian State of the Climate Report's been released, warning that the nation is continuing to warm and suffer more frequent extreme weather events, such as bushfires, droughts and heat waves. The study, which is released every 2 years by the Bureau of Meteorology and the CSIRO, uses the latest scientific climate observations, analyses and projections to provide a comprehensive report on Australia's changing climate due to global warming. The report finds Australia's climate has warmed on average by 1.44 degrees Celsius since 1910, leading to an increase in the frequency of extreme heat events. For example, there's been a significant increase in the frequency of dangerous fire weather days across the nation, especially during spring and summer, leading to an earlier start to the fire season, increasing the overall length of the fire season, and increasing extreme fire weather conditions. The study found that climate change is influencing these trends through its impact on temperature, rainfall, relative humidity, and the resulting change in the fuel moisture content. The study also found that the southern parts of the continent are seeing drier conditions with less rain, especially during the cooler months between April and October. In fact, in the southwest, the cool season rainfalls decreased by about 16% since 1970, with drought conditions expected to increase in coming decades. At the same time, rainfall has increased in parts of northern Australia since the 1970s. And while there'll be fewer tropical cyclones in the future, those that do occur will be far more severe. The oceans around Australia are also being affected by climate change, leading to significant impacts on marine ecosystems. Surface waters are acidifying and have warmed by around 1 degree since 1910, contributing to longer and more frequent marine heat waves, posing a significant threat to the longer-term health of coral reef ecosystems around the coast. Scientists found global atmospheric carbon dioxide concentrations have now reached 416 parts per million, with the rate of CO2 accumulation increasing with every passing decade. Emissions from fossil fuels are the main contributor to the observed growth in atmospheric CO2, with around 85% of all global emissions coming from fossil fuels. A new study claims having either too much or too little sleep can hasten the onset of dementia. A report in the Journal of the American Medical Association of around 20,000 people over the age of 45 found cognitive decline was more pronounced in people who on average slept for either fewer than 4 hours a night or more than 10 hours a night, compared with those who slept an average of 7 hours a night. This type of study can't show that either too little or too much sleep could actually cause accelerated cognitive decline, as the scientists observed, and why sleep might be linked to cognitive decline also remains unclear. However, the authors say people who do get too much or too little sleep may be at increased risk of dementia, and so their cognitive function should be monitored. New research by German and Swedish scientists have found that the melting of ice in polar and mountainous regions around the world could lead to an additional 0.43 degrees Celsius increase in long-term global warming. The findings, reported in the journal Nature Communications, claim that while the loss of ice cover is known to influence air temperatures, the extent of the contribution different ice sheets and feedback mechanisms make to global temperature changes has until now been unclear. So the authors used computer models to estimate the effects and found that losing the West Antarctic ice sheet could lead to an increase of 0.05 degrees Celsius, while losing the Arctic summer sea ice could lead to an increase of 0.19 degrees Celsius. The results are based on assuming atmospheric CO2 concentrations remain similar to today's 416 parts per million. And the authors note that this warming does not emerge over years or decades, but rather over centuries to millennia, although the authors pointed out that the Arctic could become ice-free during summer before the turn of the century. Your environment and your personality may be linked, according to research which will come as no surprise to anyone who's ever uttered those immortal words city folk and country bumpkins. Looking at over 3 million people across the United States, researchers found that those who lived in more mountainous areas were less trusting, caring, forgiving, and kinder, but more open to new experiences. The researchers suggest that things that are affected by where you live, such as job prospects, relationships, financial security, and mortality, can all add up to having an effect on your personality. Or it may just be that people tend to move to areas that best suit their personalities. You can make up your own mind by reading the study in full in the journal Nature Human Behavior. A new study by the Yale School of Medicine has found that cancer patients who skipped or delayed conventional treatments in order to use alternative medicines instead wound up with as much as a 5.7-fold increased risk of dying within 5 years compared to those who stuck with conventional medicines and treatment. Tim Mendham from Australian Skeptic says the findings should provoke greater scrutiny of the use of alternative medicines for the treatment of cancer.
A study that was done by researchers at Yale University, I think it was looking at the situation regarding early death from people
suffering various forms of cancer and looking at the treatments they were using to treat their cancers and forestall their death. They compared people who were looking at alternative treatments with those who were using conventional treatments and seeing how quickly they died. Quite frankly, it was fairly brutal, but it's important information to have. The alternative treatments were things like homeopathy and various sort of potions and that sort of thing. The conventional things were radiotherapy, chemotherapy, those sort of areas. So they were quite distinct. They found out that basically if you had lung cancer and you opted for the alternative medicine, you were 2 times more likely to die. If you had colorectal cancer and you went for the alternative treatment as opposed to conventional, you were 4.6 times more likely to die. And if you have breast cancer and went for alternative medicine, you're 5.7 times more likely to die within 5 years. And that's their criteria they used. So they looked at a range of people and then compared them with people the same age, same conditions, same environment, all that sort of issues, who were going through a conventional treatment. So they were basically 2 to 1, 2.5 to 1 ratio of conventional treatment as opposed to alternatives, and followed them through for this period of about 5 years to see who died, who didn't. And they then compared the two results. There's a few problems with it. They didn't actually ask which alternative treatment people were using. So it might have been one, this or the other. They also didn't necessarily follow them to see if they changed treatments. Some might have changed from alternative to conventional, and that might have changed the outcome, even suggesting that it actually might have improved the numbers for the alternative because some of them weren't doing alternative anymore, if you know what I mean. So the numbers might even have been higher. But basically, overall, the prognosis, based on not a huge number, I think they had 280 alternatives as opposed to 800 odd conventional people. And sort of,
That's still more than a quarter.
It's still, the actual overall number of people is not necessarily totally convincing, but it's interesting. It shows something worthwhile following up. And therefore, the significance of people dying of cancer is over 5 times more likely to die from alternative treatment if you got breast cancer is huge, right, within the 5 years. That should really raise a lot of flags for people who are saying that alternative is better for you, it's more natural, etc., blah, 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 sort of theories like that. It might be more natural, it's not. It might be nicer and certainly less invasive, and radiotherapy and chemotherapy are definitely invasive, but if you're using the nice treatments, the alternative treatments, you're going to be more likely to die in the long run, or even in the short run, than you would with the conventional treatments. This study showed that you're more likely to delay it longer with conventional treatments than with alternative.
And while there's life, there's hope.
Yeah, the longer you're alive, the better chances you have of finding something to cure you.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.